let me open demo, and let's look at this one. So this is extracting the loop gain. So here's an audio amplifier, and I interject signals to extract the open loop transfer function while it's operating closed loop. As you simulate this, this is going to be one plot. Here I'm looking at the current gain, the voltage gain, and then they convolute together into a net loop gain per our David Middlebrooks 1975 paper on feedback loops. So if we uncomment this thing here, so it's going to now do a step, and so it's running multiple simulations. So you can see all these simulations. I'll get this out of the way for a second. So here you have all these different simulations. Let me just make a copy of this. And let's say I just want to look at, here you'd want to use the step tool. So here we press F6. Let's just look at that one, apply. And over here, we use the step tool with F6. Let's just look at that one, apply. And there you can see the two different simulations plotted in different waveforms. But what's interesting is that in this, I have these dot measure statements which actually measure the phase margin. These are the statements here. Let me uncomment this for a second and just look at the behavior of these two this phase margin. It gives you the phase margin here. It's 73 degrees. And the crossover frequency is, looks like it's 400 kilohertz. All right. So is that right? Let's just, yeah, 450 kilohertz. It's a real good audio amplifier. Exceedingly low harmonic distortion. But, you know, the phase margin is actually like basically, it's not a good quantum number. It kind of varies all over the place because in an AB amp like this, as you switch from the high side, the low side to running both, the phase margin varies dramatically. So let's look at the phase margin as we change the output voltage. So I'll uncomment that. And then I'll plot these phase margin numbers. So these are all these steps. And once that step is done, this now is plotting phase margin with the output voltage.
Right.
And you can see, yeah, you get really good phase margin when the output is centered. But as you get close to rail, you see you lose phase margin. You're down to less than 20 degrees. And you know, you've certainly, if you've played with audio amplifiers, you've certainly seen audio amplifiers that have a nice sine wave till they get the positive rail, then they oscillate, then they get away from the positive rail, they stop oscillate at the positive rail. You know, you've seen amps do that, and this lets you quantify it very, very well. In fact, if you really zoom into this central region, you'll see that there's a lot of structure in exactly how the high side and low side varies. The phase margin varies wildly within just tens of millivolts of the output being centered. I do want to touch on what Pete was talking about a second with power traction inversion, if I'm allowed to. And this is a driver board that's fully modeled in Qspice. These are all hierarchical schematics. This is actually in C. You say what frequency and what amplitude you want, and then it dithers out the control signals for all these gates. But everything is modeled. Every power supply, you know, the whole thing is modeled. Every component of the board for this 300 horsepower traction inverter, and you can watch the thing simulate with the FETs, you know, with the wide band gap FETs, and you can watch this thing drive the three-phase motor controller, and then it's a chop controller, so the chop frequency is also dithered between them all. So, yeah, we could simulate the whole. You know, eventually I want to add motors so that we can simulate from the battery chemistry to the rubber. That's the goal.
Wow.
That's what I'd like to be able to do.
And is this particular demo project included in the current release?
No, this was actually prepared for an in-house presentation at a local EV car manufacturer.
Right.
So this one I'm not including in the demo. There's a lot to explain and what it's doing, and I don't want to do that right now. Also, it's using parts that aren't even announced yet for the device. It's using a variation of the Cascode, which